Hi everyone, my name is Andrei and today I'm going to present our work on a topic of explaining medical image segmentation, more specifically explaining cancer segmentation through classification. Clinically, early lung cancer detection is extremely important, but it remains difficult because CT imaging is complex and expert radiological annotations are expensive and limited. From a machine learning perspective, however, this means that we often have small datasets, strong class imbalance, and very few high-quality segmentation labels. On top of that, neural networks are often treated as black boxes. So even when a model predicts cancer correctly, it can be hard to know whether it was focusing on clinically meaningful regions or just on spurious imaging patterns. Rather than training a full 3D segmentation model, our approach is to train a lighter 2D CNN for slice-level cancer classification. We then use GradCam to identify the regions that drive positive predictions, filter those heat maps, and stack them across slices to reconstruct the 3D segmentation volume. So the key idea is that explanations are not only focused on post-hoc interpretation, but they become actionable evidence, helping us segment the right thing for the right reasons. Training the CNN classifier is a multi-stage process. Starting from regional city slices, we construct two datasets, a truncated version which has a more balanced distribution between tumorous and non-tumorous slices, and a second version which contains all of the images. Starting with the truncated dataset, we train the classification head of the CNN classifier. For stage 1, we then unfreeze the backbone and train it jointly on the truncated dataset, and only then in the first stage do we use all of the images to train the final classification model. The segmentation pipeline that goes as follows. Starting with a series of CT slices, we pass them through the CNN classifier to get a sequence of binary predictions. Those predictions, alongside their corresponding GradCam explanations, go through a filtering and thresholding stage, which then produces the final segmentation masks. For some experimental results, all tested architectures performed well in terms of classification scores, but notably different in terms of explainability. Moreover, as mentioned previously, the heat maps are filtered before becoming the segmentation maps, and this is done in order to ensure that we only use the high confidence areas. For segmentation, while classification performance is still important, the quality of the mask is also dependent on the model's overall behavior, favoring more focused and localized responses. Consequently, models with large receptive fields perform notably worse in terms of downstream segmentation performance. Some key takeaways. We've proven that explanations can localize. GradCam heat maps show potential not only for interpreting the predictions, but also for producing robust segmentation masks. Secondly, stability beats complexity. Our proposed 2D slice-based pipeline proved more reliable than our previous work on direct 3D training. Thirdly, and arguably most important, trust needs evidence. Being able to highlight clinically meaningful regions makes the model more transparent, but also more trustworthy. For our full paper, you can scan the QR code, and thank you very much for the support from the ENFIELD project.